Well, then with this video, we're finally to the end of geometric sequences and series. And this next bit we're looking at is the sum to infinity of a geometric series. I'd just like you to think about that question there that I'm floating about the screen. What happens if you keep multiplying any whole number by a number between 0 and 1? You would have first done that at Key Stage 3 in Year 9. What you should remember is each term is going to get smaller and smaller and smaller. So just try and recalculate it. Try, I don't know, 2 multiplied by 0.4, 0.4, 0.4 and so on. So how would that affect the sum of all of those numbers? So if I was summing a geometric series where my ratio was a number between 0 and 1, how would that affect, say, my sum of the first 10 terms, or my first 20 terms, or my first 50 terms? Okay? And to understand what I'm getting at, what I'd like you to think about is, imagine if I have a first term of 3, and a common ratio of 0.2, a number between 0 and 1. Okay? So if we just generate the first couple of terms of that series, the first one will be 0.6. Well, sorry, the first one is 3. 3 multiplied by 0.2 will be 0.6. Then it'll be 0.12. Then it'll be 0.024. Then another smaller number, 0.0048. Right, I want to generate a few of these, so we just shift this slightly along. 0.00096. So each number is getting tinier and tinier and tinier, look. So imagine if I wanted the sum of the first 5 terms, 10 terms, 15 terms, but I want them all rounded to 1 decimal place, or 2 decimal places, for example. Is there any point in carrying on with these numbers? Are they having any effect at all? When I get down to this point, look, and I've got 0.0000 before my non-zero digits start, those numbers are so minute. Are they having any real effect on my sum? Okay, so let's just work out the sum as we go along, look. So by the second term, my sum would be 3.6, then 3.72, then 3.744, then 3.7488. So let's just scroll across. I'd have 3.74976. 3.749952. And can you see, look, it's not having any effect really now on these numbers, is it? 3.749904. So I'm rounding to like 4 decimal places there. The last 3 terms of calculated would be the same. Okay? So what we could say is 3.75 would be a decent answer as my sum of that series. Okay? The idea of a sum to infinity means that because each term is getting smaller and smaller and smaller and smaller, if we multiply by 0 and 1, after a certain number of terms, that number is so minutely small that it's not really having any effect on that term, okay, on that sum. So when we get to a certain point, like close to infinity, our answer would always just be the same effectively. Okay, so that's what a sum to infinity of a geometric series is. It only works if our ratio is between 0 and 1, because it's using that idea of a limit. Each term that we're adding is getting smaller and smaller and smaller. So our sum is, rather than getting bigger and bigger and bigger and bigger, like it would in the ones we were looking at in the last exercise, this time it would actually just get closer and closer and closer and closer and closer to a certain number. Okay, so let's look at what our formula would be for the sum to infinity. So this is the sum to infinity. Okay, this works when r is small, or actually more accurately, it works when r is between 0 and 1. Actually, it works if r is between 0 and negative 1 as well, because if it was 0 and negative 1, it still get smaller and smaller. It's just it would go from alternate between negative and positive, negative and positive. An easier way of writing that is we say the modulus of r is less than 1. So those two straight lines around the r, it just means if it was a negative r, we'd treat it as being a positive one. Okay? So as long as that number, the common ratio is between -1 and 1, is what you want to think of it as. Okay? So if we take our sum formula, we've got a brackets r, 1 minus r to the power n divided by 1 subtract r. So I've just used that formula because the r is going to be between 0 and 1. So I want to be left with a positive number on the bottom. That's the only reason. Okay? So what we're going to say is as n approaches infinity, which is the maths way of saying as n gets really, really big, all right, r to the power n is going to get really, really, really tiny. So it's going to start going towards 0. All right, just think if you did 0.1 to the power 10, that's a tiny number. Okay, so as the bigger that power gets, the r to the power n term goes towards 0. All right, so we could treat it as it actually does go to 0. So what we would say is as n approaches infinity, the sum approaches a divided by 1 subtract r, because that r to the power n would have gone to 0. So you just add a on the top. So we say our sum to infinity is equal to a divided by 1 minus r. But it only works if r is a tiny number. So if r is between -1 and 1, then we can find the sum to infinity. Okay? So let's try an example. So find the sum to infinity, if it exists, be careful with that phrase, of the following series. So let's do 10, subtract 5, add 2.5, subtract 1.25, add ... I should have put in there. And the other one we look at is 1, add 2, add 4, add 8. Okay? So first of all, let's do the one on the right-hand side first of all. Our common ratio is 2, look, because we're multiplying each one by 2. So it doesn't fit that criteria of it being between -1 and 1. So it doesn't exist because r is a big number. Okay, so it's not between -1 and 1. So you want to be careful with that phrase, if it exists, because it doesn't exist for every single sequence. Now in this one, on the left-hand side, obviously it is going to exist because I want to do one example with you, but it does. But a is equal to 10, the first term is 10, and r is -1/2, look. So I'm halving each number, and also the signs are alternating. So because my sum to infinity, my r, it does lie between -1 and 1, I can use the sum to infinity formula. So that'll be a, which is 10, divided by 1 subtract r, which is -0.5. So that's going to be 2, stick onto your calculator, and you get an answer of 20/3. Okay, leave it as a fraction, or round it to a degree of accuracy if the question asks you to. Okay, and that is it. Off you go with exercise 7e, the sum to infinity of a geometric series, only if it exists, remember. Okay, good luck.